You know that feeling, right? You pick up two magnets, and you can feel that weird, invisible cushion pushing them apart. Or even better, that sudden, super satisfying snap when they pull together. It seriously feels like magic. But nope, it's pure science.
Yeah, it's not magic, it's physics. But what is actually going on in that empty space between them? I mean, what is this invisible force that can just reach out and grab something? Let's dig in and figure it out.
All right, so the first piece of the puzzle we've got to understand is this idea of a field. It's a word that gets thrown around a lot in science, but it's absolutely crucial for understanding how forces like magnetism can even work without touching anything. So what is it? Well, to put it simply, a magnetic field is just a region of influence. A magnet literally changes the space all around it. Anything that can be affected by magnetism that wanders into this zone is going to feel a push or a pull. But here's the catch. It's totally invisible. So how in the world are we supposed to picture what's going on? Well, to see the invisible, physicists came up with these things called magnetic flux lines. And what you're looking at here, this is not your fridge magnet. This is a simulation of the crazy complex field inside something called a quadruple magnet. This is the heavy-duty stuff they use to steer particles in giant accelerators. Just look at it. The lines show you the direction of the force, and check this out. Where the lines are all bunched up together, that's where the field is super, super powerful. Okay, so we've got this invisible field, this area of influence around a magnet. But where does it even come from? What's creating it? Well, the answer is actually shockingly simple. And it connects two of the biggest forces in the universe. This is the big secret. Every bit of magnetism in the entire universe comes from one thing, a moving electric charge. That's it. If a charge is just sitting still, you only get an electric field. But the second it starts moving, bam, a magnetic field just appears out of nowhere. They're like two sides of the very same coin. And look, this isn't just some theory. It's a fundamental rule of physics. A bunch of charges flowing together is what we call an electric current, right? And as this quote from Cambridge says, currents create magnetic fields, period. And that's the whole trick behind a permanent magnet. There isn't a wire inside, but you've got billions and billions of tiny electrons all spinning and orbiting inside the atoms, and they're all lined up, creating one big, powerful, permanent magnetic field.
All right, so when people talk about magnetic fields, you'll hear two words get thrown around that can be kind of confusing: strength and flux. They're definitely related, but they mean different things. And if you really want to get what's going on, you got to know the difference.
So let's think of it like this. Magnetic field strength is all about a single point. It's like asking, how strong is the pole right here in this one specific spot? But magnetic flux is about the big picture. It's asking, how much total magnetism is passing through this whole area, through this entire loop? One's a snapshot, the other's the total. Okay, to make this crystal clear, I've got a great analogy for you. Just imagine the magnetic field isn't a bunch of invisible lines. Instead, picture it as a whole storm of arrows, all flying in the exact same direction. Okay, stick with me on the arrow thing. The strength of the field, that's just how powerful a single one of those arrows is. Easy enough. Now the flux, that's the total number of arrows you can catch in a hoop if you hold it up. And here's where it gets really clever. What happens if you turn that hoop sideways to the arrows? Well, fewer arrows are going to pass through it, right? Maybe even zero. The flux just went way down, even though the arrows themselves are still flying just as hard as they were before. See the difference? Right, so a moving charge makes a magnetic field. Got it. But what happens when a different moving charge comes flying into that field? Well, it's going to feel a force, but which way is it going to get pushed? Up, down, sideways? This is where it gets interactive. The magnetic field from one group of moving charges actually pushes and pulls on other moving charges that come near it. It's totally a two-way street. So there's a name for this. It's called the Lorentz force. Now, don't get hung up on the formula. Just look at what it's made of. The force you feel depends on the charge, how fast it's going, and how strong the field is. But honestly, the coolest part is the angle. Get this. If a charge moves perfectly parallel to the field lines, nothing happens. Zero force. You have to actually cut across the field lines to feel that push. Now, the direction of this push is, well, it's a little weird. It's not forward, it's not backward, it's at a right angle to both the direction the charge is moving and the direction of the magnetic field itself. Yeah, I know that sounds super complicated, but don't worry, there's a really easy cheat code for it. It's called the right hand rule, and you can literally do it right now. Okay, take your right hand, your thumb,
Point that in the same direction the charge is moving. Your fingers? Point those in the direction of the magnetic field lines. Now, the direction your palm is facing, like you're about to give a high five, that's the direction of the force. Simple, right? It's like you have a built-in calculator on your hand for figuring this stuff out. And that simple little hand trick, it governs everything from how tiny particles behave to how giant machines work. So why does any of this theory matter in the real world? Because when you scale this stuff up, magnetism becomes an unbelievably powerful and, honestly, a pretty dangerous force.
Just to give you some perspective on this power, the Earth's magnetic field, the one that protects our entire planet from solar radiation, is about half a Gauss. Now, a strong neodymium magnet, one of those little silvery ones you can buy online, it can be up to 20,000 Gauss. That's 40,000 times stronger. One is a planetary shield, the other can shatter a bone.
And I'm not kidding about the danger. These things are no joke. They can shatter like glass if they slam together, sending sharp metal fragments flying. They can pinch your skin so hard they'll draw blood or even break a finger. They'll instantly wipe a credit card or a hard drive. They can mess up your phone or your watch. And for someone with a pacemaker, getting too close is a life-threatening risk. This is the kind of physics you really have to respect. But that same raw, immense power, when you learn how to control it, that's what drives our most advanced technology. We're back at that quadrupole magnet again. Scientists take these same bone-breaking forces and use them to steer tiny particles at almost the speed of light. It's how we smash atoms apart and learn about the very fabric of reality. So think about that. We started with a simple toy magnet and we ended up at particle accelerators. But it all boils down to one simple idea. Moving charges create fields, and those fields push on other moving charges. It really just leaves you with one final big question, doesn't it? If a simple moving charge can create this incredibly powerful and complex invisible force, what other fundamental forces are out there, shaping our entire world in ways we can't even see?